Every so often a number pops up online that seems impossible, something that makes even seasoned tech enthusiasts do a double take. Lately, the tech world has been buzzing about a so-called 0.2 nanometer chip, a claim that's spread like wildfire across forums and headlines. The idea sounds like pure science fiction, a leap so massive it would make today's fastest processors look like relics from a bygone era. But let's pause for a reality check. 0.2 nanometers is actually the diameter of a single silicon atom, the very building block of all modern chips, and the smallest unit you can get in silicon. So, are we really building transistors the size of a single atom? Not quite. In fact, the laws of physics make that nearly impossible with current technology. The truth is, when tech headlines tout numbers that seem too good to be true, they usually are, or at least, they're not telling the whole story. These numbers often refer to marketing terms, not actual physical measurements. The semiconductor industry has always been about making things smaller and faster, following Moore's law, which predicted the doubling of transistors every couple of years. But as we approach atomic scales, the rules of the game change dramatically. Quantum effects, heat, and manufacturing limits all come into play. A 0.2 nanometer chip isn't a physical object with atom-sized components. It's more of a marketing headline than a literal breakthrough. Companies use these numbers to signal progress, even if the reality is more complex. To understand what's really going on, we need to look at where the industry stands, where it's headed, and the challenges ahead. The journey to smaller chips is filled with innovation, but also with new obstacles. The story of the 0.2 nanometer chip isn't about a single breakthrough, it's about the end of one era and the dawn of another. Let's dig in and separate the hype from the real science. To understand the hype around chip technology, let's rewind the clock and look at how we got here. For decades, the number in a chip's name, like 14 or 10 nanometers, referred to the size of a crucial part of the transistor, the building block of every chip. Smaller numbers meant faster, more efficient chips, and the entire industry raced to shrink these features as much as possible, year after year. This relentless progress took us from room-sized computers and bulky desktops to the powerful smartphones we carry in our pockets today. But as we approached 14 and 10 nanometers, the laws of physics started pushing back. Making things smaller became not just difficult, but incredibly expensive and complex. The numbers printed on the box stopped matching the actual physical sizes inside the chip. The reality became much more complicated. Now when you see 7 nanometer or 3 nanometer on a product, it's more of a branding tool than a true measurement of any one feature. Today's chips, like Apple's A17 Pro, are technological marvels packed with billions of transistors, but the nanometer label is mostly a way to signal a new generation of improvements. The number has become a marketing term, a shorthand for better and newer, rather than a precise measurement you can verify with a ruler. This shift in language is crucial to understanding why 0.2 nanometers is even being discussed today, despite sounding almost impossible. The industry's language has changed, but the drive for progress and innovation remains as fierce as ever. Smaller numbers still suggest better chips, but not in the straightforward way you might expect. It's about more than just size now. It's all about performance, efficiency, and new features, not just how tiny the parts are. And that's how we end up with the wild, headline-grabbing claims of 0.2 nanometers, a number that's more about progress than physical reality. So, what does nanometer mean now? It's a performance density metric, a label for a new generation of manufacturing tech. When TSMC or Samsung announces a new node, it's about better performance, efficiency, or packing more transistors into the same space. The old way of measuring just one part of the transistor stopped telling the whole story. New structures like FinFET, where the gate wraps around the channel, helped keep Moore's law alive, even as physical shrinking slowed. The nanometer label became shorthand for a suite of innovations, not a literal size. Each company defines its own node, making the numbers more about branding than measurement. This confusion opens the door for futuristic claims, like 0.2 nanometers. In today's chip world, marketing has replaced measurement. The number is a symbol, not a spec. While 0.2 nanometers is sci-fi, the real frontier is the 2 nanometer node. TSMC, Samsung, and Intel are investing billions to reach this milestone. The old FinFET design is maxed out, so the industry is shifting to gate-all-around, GAA, transistors, where the gate wraps around the channel on all sides. This new structure allows for even better control and efficiency. Companies are racing to perfect their versions: TSMC's N2, Samsung's SF2, and Intel's RibbonFET. Intel's 20A process, A for angstrom, or 0.1 nanometer, is their take on the 2-nanometer node. These advances require massive new factories and will power the next generation of AI, smartphones, and high-performance computing. The first 2-nanometer chips are expected around 2025-2026. This is the real cutting edge, far more realistic and exciting than the mythical 0.2-nanometer chip. The future is being built now, just not at the atomic scale. Here's the reality check. A 0.2-nanometer chip is impossible with current physics. A silicon atom is about 0.2 nanometers wide, but a transistor needs multiple atoms to function. Even if you could build a transistor just a few atoms across, quantum tunneling would make it unreliable. Electrons would leak through barriers, making it impossible to turn off. At these scales, heat and instability become unmanageable. We're already struggling with heat in today's chips. At 0.2 nanometers, it's a meltdown. The limits of silicon, quantum effects, and atomic size mean we can't just keep shrinking. Building a true 0.2 nanometer chip isn't just hard, it's a physics problem. We'd need entirely new materials, designs, or even a new model of computation. So, why do we hear about 0.2 nanometers? It comes from industry roadmaps, projections, not promises. These numbers, like A2 for 0.2 nanometers, are placeholders for future performance goals, not physical sizes. They represent the improvements we'd expect if we could keep shrinking, even though we can't. It's marketing shorthand for a future generation of technology that will look nothing like today's chips. The industry uses these signposts to guide investment and innovation. The 0.2 nanometer claim is an extrapolation, a way to keep Moore's law alive on paper. It's about finding new ways to deliver performance, not building atom-sized transistors. If shrinking silicon is a dead end, what's next? The answer: new materials and 3D stacking. Researchers are exploring two-dimensional materials like graphene and molybdenum disulfide, which are just atoms thick and could enable much smaller, more efficient transistors. Another breakthrough is chiplets, smaller chips stacked or connected together, each specialized for a task. This modular approach allows for more power and efficiency without shrinking everything to the atomic scale. AMD and Apple are already using chiplet and advanced packaging tech. The next step is true 3D stacking, bonding chips directly on top of each other for even faster communication. Beyond that, photonic chips and quantum computing could redefine what's possible. These innovations are the real path to 0.2 nanometer equivalent performance. These breakthroughs aren't just theory, they're happening now. IBM's 2-nanometer chip prototype proved new nanosheet technology works, packing 50 billion transistors on a fingernail. Researchers at MIT and Stanford have built working transistors from 2D materials and bonded them to silicon wafers. Chiplet and 3D stacking are already in products from AMD and Apple, with even more advanced versions on the way. Photonics is entering data centers, enabling ultra-fast chip-to-chip communication. Each advance, 2 nanometers prototypes, 2D materials, advanced packaging, is a step towards 0.2 nanometer equivalent performance. The future is being built in labs and fabs right now. The journey is real, even if the headline number isn't. So, when will we actually see chips that deliver 0.2 nanometer level performance? It's a question that sparks excitement and curiosity across the tech world, as engineers and researchers push the boundaries of what's possible. Realistically, this level of advancement is at least a decade away, if not longer. The journey to such tiny scales is filled with technical hurdles and requires breakthroughs at every step. 2-nanometer chips are expected to arrive by 2025 or 2026, marking a major milestone in chip manufacturing. After that, we'll see the emergence of angstrom-scale nodes, which will push the limits of miniaturization even further. Achieving 0.2 nanometer equivalent performance will demand mainstream adoption of 3D stacking, entirely new materials, and revolutionary design approaches. These advances are likely to arrive sometime in the 2030s as the industry evolves and new technologies mature. The first chips, built with 2D materials, like graphene or transition metal dichalcogenides, may appear in the early 2030s, but initially, they'll be used for highly specialized functions, not for general-purpose computing. By 2035, we might see the debut of A2 chips. These will be complex, 3D integrated systems that combine silicon, 2D materials, and even optical links for lightning-fast data transfer. The impact of such technology? It will be nothing short of profound. Imagine phones running powerful AI locally, lightweight AR glasses that blend seamlessly into daily life, and ultra-efficient data centers that use far less energy. The 0.2 nanometer chip is, in many ways, a mirage. A destination that doesn't truly exist in a literal sense, but the relentless pursuit of this goal is what drives real, tangible innovation in the industry. The journey itself is what matters most, pushing us beyond the limits of silicon and into a bold new era of computing technology. You may never actually own a literal 0.2 nanometer chip, but you'll absolutely benefit from the breakthroughs and innovations it inspires in the devices you use every day. The next great leap in performance is on the horizon, and when it arrives, it will transform the world in ways we're only beginning to imagine.